If you're designing high-performance systems that require both high throughput and cache coherency, you're going to want to think about including C6 in your design. Synopsys has got an excellent C6 solution based on our DesignWare C6 IP. Let me show you a demo. So we can start over here on the root complex side. This big box here is our HAPS 80. It's our prototyping system that contains our root complex controller in FPGA form inside here. And controlling this whole thing is our ARC board, which is this little board on top here. And this is running Linux. This is enumerating the PCI Express system, both the RC side and the endpoint side. Then it comes out of the controller, and of course it has to go to a physical layer, so it goes to a PHY daughter card. And that's this card you can see here. It's plugged in. It's got another FPGA there. It's got our PCS layer, which in this case the pipe interface or a near pipe interface for C6. And then the PHY itself is in over here. So now we come over to the other side and we come across what's really kind of a very small channel. It's really just a connector. This is a standard PCI Express connector. We're coming from this PHY card to this other PHY card here. This one is still got the 25 gig PHY daughter card, but this is connected to another HAPS 80 system. This one is running our endpoint controller. So the complete system then runs from the root complex through the two PHYs, across this little channel here, mostly made of the connector, and into the endpoint. Okay, so let's take a look at our C6 25 gigatransfers per second demo. To start off, we're looking at a rate change loop. So what's happening is we're cycling through the data rates. Right now we're at 25 gigatransfers per second, and you can see the total bandwidth here of this link at 2699 megabytes per second. And now it's cycled to 2.5 gig. And then after operating at that rate for a little while, we'll cycle through to the next PCI Express rate, which is 5 gig. You'll see that in a second. There we are. And you can see on the bar graph here, you can see we just went from this rate here up to 465 megabytes per second. And then we'll soon jump to 8. So now you can see we're at PCI Gen 3 speed at 8 gigatransfers per second. And now, after that, we'll jump right up to 25 gigatransfers per second, which is the C6 extended speed mode data rate. And there we are. So now I've stopped the rate change loop, and we are operating continuously at 25 gigatransfers per second. You can see again the data rate here, close to the theoretical maximum that we would expect after taking into account the 128, 130 encoding decoding and the overhead for the packets, etc. We're close to 2700 megabytes per second. And this in the green, we're seeing the endpoint. There's two sides to this link. On this side, we can see the RC, or the root complex, and of course the data rate's the same since we're just passing data from one side to the other. So now what I'd like to do is, from the endpoint, I'm going to go ahead and take advantage of one of the nice features we've built into our controller, which is the error injection capability. So we have a lot of different kinds of errors that we can inject, and when I come over here to error injection, you can see there's several different kinds at different levels of hierarchy. There's some here, there's some over here, here's some at kind of the PHY level where we can mess with the encoding and decoding, etc., and even some over here generating duplicate TLPs, etc. So the one that I like to show is over here. It's TX new TLPs LCRC error. So what this means is that every new TLP or every new packet is going to be sent with an error from the endpoint to the root. So what that means then is when the root port gets the packet, it's going to knock the packet saying that it's no good. And then the replay buffer in the endpoint is going to send that packet again. Now because that's automatic and because we're not corrupting that packet, the second time it's sent, it'll come through without an error. So the net effect that we'll see on the bandwidth, and you'll see it happen almost instantaneously, is that it'll drop a little bit less than half. There's some overhead and some other things. But essentially we're cutting the bandwidth in half by injecting these errors. So let's go ahead and do that. Start the errors. It's come on, and then we'll go back to the performance view. And then if you look over here, what's happening, this is propagating across now in time. We've dropped to 1265. So we've dropped from 2699, 1265, a little more than half for our throughput. So from the root port perspective, let's take a look at the error counter here. So if I go in here and go to the error counter, what you'll see is these registers that we've set up to count the errors. They're seeing the bad TLPs come through. they're seeing the LCRC errors, which is the kind of TLP error that we're creating, and then we're getting these NACT packets. So here we're seeing 255 for each one of these because it's a 256-bit counter and we've maxed them out. So what I'm going to do now is go back to my endpoint here, back into the error injection, and I'm going to stop this error injection. Okay, so now I've stopped the error injection. If I go back to the performance view, you'll see that we right away have recovered the full bandwidth. It's one of the reasons it's a nice demonstration. It's non-destructive. Doesn't bring the link down, just kind of kills the bandwidth. So it's one of the nice RAS DES features that we can employ. And again, there's a lot of other ones. So you can see the bandwidth is back to normal. Now I'd like to show one other demonstration. If you look up here in this corner, we're using packets that are 1024 bytes. That's our payload size. So what we're going to do now is reduce that. I'm going to run a script that's going to reduce that packet size. And what we're going to see is that that actually affects the throughput. Why does that happen? Because the packets have some overhead. You think about it. They've got a fixed header, a certain amount of bytes that's on there. And it doesn't matter how big the data is, you're going to have that overhead. So for small packets, I'm going to drop it to 128. We're going to see a substantial drop in the throughput here. So let's go ahead and do that. I've got a script I can run. And we're going to change the payload size to 128. And let's see what happens. You can see we've dropped now to 2033. That's pretty substantial. That's about 75% of the throughput we were getting. And we didn't change anything in the system configuration. All we did was change the payload size. And this too is reversible. So if I go in here now and go back and run the 1024-bit again, I'll very quickly get back to my full payload. Okay, so I've stopped the rate change loop, and we're now running at CCIX 25 gigatransfers per second data rate. You can see we're steady here at close to the theoretical maximum, accounting for the encoding, decoding, 128, 130, as well as the packet overhead. We're here at 2699 megabytes per second. So again, this is something that designers want to pay attention to. You want to make sure that the payload size is set correctly so that you can maximize your throughput if that's something that's really important to you. So in this example, again, I went from 1024 to 128. The demo you've just watched is a complete end-to-end C6 solution based on Synopsys DesignWare C6 IP. It's available today, and it supports multiple foundry nodes, including the most advanced FinFET technologies. We've got a high-performance system that can give you close to the theoretical maximum throughput, and we also support multiple interfaces so that you can plug into an ARM coherent fabric as well as your own coherent fabric if you've got that design. Thanks for watching.